morning, everyone. I'm pleased you're able to join us for today's Ask the Experts presentation sponsored by Qualmark. I'm Cami Marsh, Qualmark's Global Marketing Manager, and I'll be your moderator today. And today's Ask the Experts broadcast is being recorded. A link will be emailed to you should you wish to replay any portion of the presentation. We encourage you to go back and listen and review and share it with your colleagues. Questions can be submitted at any time during the broadcast by text using the chat screen, and we will answer as many questions as time allows at the conclusion of the presentation. But please send those in as you think of them. And this is being broadcast over broadcast audio, so you don't have to dial in. You can listen through your computer speakers, but there is a dial-in number available should you require that. Qualmark Center of Excellence is hosting today's presentation, Connecting HALT to Program Goals, with our guest speaker, Mr. Adam Barrett from Apex Ridge Reliability. Adam is a reliability engineer with extensive experience in program strategy, accelerated testing methods, HALT, HAST, QALT, ALT. In the course of his work, he has advanced products in the field of robotics, medical device, consumer electronics, and heavy equipment. At this time, I'd like to introduce Adam Barrett to get the presentation started.
Controls issue with the audio, so.
Thank you. Please proceed.
Okay, fantastic. All right, Cami, I'm sure you did a very nice introduction. I couldn't hear it, but everybody, thank you very much for joining us today. I'm Adam Barrett. I am the founder and lead engineer at Apex Ridge Reliability, which is a reliability consulting firm. We specialize in being able to tailor reliability solutions for you, your company, and your project. We always start off by assessing you, your current process, and your goals, and create a team and processes that will get you to your goals as quickly as possible. I'm very excited today to be talking with you about HALT and how it integrates into the product development process, and looking specifically also at the return on investment of HALT. We've done some previous seminars which go into the details of the HALT process and how it improves the product. But it's also very important to also understand and be able to communicate to other parts of the organization, the business parts, the marketing, sales, and project management, about how HALT will help them with their goals, because we're running a business and we want to ensure that the processes we're doing are benefiting the business. So we have a diverse audience today, and I want to make sure everybody is in sync. So I'm going to talk a little bit about HALT itself and what it does, and ultimately end up discussing a case study looking at ROI. So let's talk about HALT a little bit. So over the last 30 years, HALT was initially something that kind of had a small cult following within the reliability community, where now has spread to all industries, and is something that has been established to show with electronic, mechanical, and other complex devices to create significant improvement in the design in a very short period of time. So we want to communicate value. So what's the value to the managers, management, manufacturing even, the quality, and to the business unit? So let's take a look at that. So HALT improves the design by quickly identifying the product's failure modes. The results are delivered in less than a week. This process is only a few days for each iteration you do. It offers insight into the product functionality that usually is achieved with many years of production run and field data acquisition. So there is that process of the product after release becoming mature by studying the field usage. Well, here's an opportunity to take that maturity process and compress it and bring it into the early stages of product development. So if it can deliver that, you can see how powerful it is. Now, even as a reliability engineer, I will tell you that you don't want to make your product too reliable. You want to find that point of optimum sales. And this is going to, of course, there'll be a lot of factors associated with this, what functionality you put in the design, your cost point, and your reliability. You should know your goals in advance, and you should move towards them. If it's too reliable, the product will be too expensive for your target market. You have a target price you want to hit. If it's too reliable to get it very extremely reliable, you'll have late product delivery because of how long the engineering process goes. And you'll also have loss of sales because you might be behind your competitors in technology development because you're doing slower product iterations. Now, of course, on the other end, if your product is not reliable enough, you have a high field failure rate, very high warranty costs, and you lose sales due to customer dissatisfaction. So let's take a look at just some examples. So let's take Yugo, Toyota, and Rolls-Royce. These three companies are in three very different spots in the scale. Yugo went out of business. Their products had the lowest cost point, but they were so unreliable that it wasn't worth it. Rolls-Royce was purchased for brand name, so effectively went out of business, their automotive division. You still can buy Rolls-Royce, but it's effectively manufactured by other companies. They had practices where they had a spec for an optically polished windshield, so they had to discard 13 windshields for every one that was actually incorporated in a product. Well, you have to pass that cost on to the customer. Does the customer care to have a windshield that's optically polished? No, because in the first couple months you're going to have stone chips in it, and it's still going to be an acceptable product, but you will have lost that high precision. So there's no point creating an extra cost and developing to that level. What we have here is a very famous graphic for reliability. It's the Bathtub Curve. This is a great graphic to understand because so much of reliability discussion can be based on it. So I want to take a moment to cover it. We will come back to it later when we are going to be talking about some of the principles. What you can see here is that there are three distinct phases to this curve. The first is the infant mortality portion. This is driven primarily by quality failures. So you can see on the y-axis there you have the failure rate, and at the bottom is time. And if you have a population that you manufacture and distribute, this will be the percentage failures for that population that will occur over its time. So it's obvious then in the beginning that quality defects, which tend to come to the surface very early on, will be driving the initial part there. But they will very quickly be discovered and removed from the population. At that point, you're in the useful life period. And the useful life period is the period that reflects that reliability number that's advertised for the product. When you say a product has 99.9% reliability, you're talking about the steady state failure rate that's during useful life. And this is driven primarily by stress failures and variability in usage conditions. You will then get into the wear out phase. And this is a very predictable change in the failure rate. This is based on wear out. And if you studied your product, you'll know when things are going to be consumed. So effectively bearings, let's say behavior will change at a certain point, they'll wear out. So now HALT. Let's take a look at the definition. This is the definition by Dr. Greg Hobbs, who is considered the founder of formally creating the HALT practice back in the 80s. Now you see here, HALT stands for Highly Accelerated Life Test, but I crossed out the word life and put limit. And Dr. Hobbs actually, openly I heard him say this in a conference, regretted using the word life in the name, because the intention of HALT is not to predict life. The intention is to find the limits of the system and how it fails under extreme stresses. So I like to call it highly accelerated limit testing, and I think if he had an opportunity to recall his original acronym, he may do that as well. So the definition. It's performed to ruggedize the product and obtain large margins over the expected in-use conditions, uses all stresses which can cause relevant failures, and stresses are not limited to field levels or stresses. That last sentence is critical. This is part of the core principle for HALT. Stresses are not limited to field levels or stresses. This means that you will take stresses and run them to as far of an extreme as you can until you see both functional limits where the product doesn't perform as intended and full destruct limits where the product does not recover from the failure mode. And not only might these stresses be the type of stresses it sees, but these can be stresses that it would never see. So a product that, let's say, sits on a counter somewhere, either in a lab or at home on a kitchen counter, you might use vibration to expose failure mode. And this is a difficult concept to initially embrace if you're used to testing that's associated to demonstrating how the product will operate in its normal conditions. So there will be a pushback initially at the idea of using vibration, but this vibration may expose failures that could be associated to other defects in the product. So you're going to get to see the failure in good product that normally you'd have to have a defective product to see. So if we take a look here at a simple chart of the stress on the bottom axis. And we look at, we have the operating specification there. This would be the stresses that are expected to occur in the field and what's designed to. You then have the upper and lower operational limit. When you hit these stresses, the device doesn't perform as intended anymore. It may not completely fail, but it's not performing as intended. And then you hit the destruct limits. This is where even after you remove the stress, the product no longer is working as intended. So our design margin is the difference between the operating specification and the upper and lower operational limit. Now, we know that for a population, there's going to be natural distribution around this. This is our very familiar bell curve, which for any population, you're going to have this kind of distribution around any parameter. Now, you can see there the operational specification and that distribution around it. That green area is the conditions that the entire population operates in. But you can see now with the actual upper operational limits for the actual produced products, you're going to have some overlap with those two curves. And that's going to be the portion of your population that fails. So that green section, the original green section there is the entire population. The red section is the percentage of failure that you have because of these two variabilities that overlap. Now after HALT, what you'll see is the design input you got from the HALT testing and the improvements that you made have pushed out those operational limits and destruct limits farther out. Now look at that overlap between the operational limits and the operating specifications. It's very small. That's now your new failure rate. So it's greatly reduced compared to the original. So if we go back to the bathtub curve, what would this look like in the bathtub curve as far as improving the reliability performance of the product? So for the infant mortality stage, HALT reduces sensitivity to quality manufacturing issues. And you can do a derivative screening process in manufacturing called HASS, highly exerted stress screening, which I'll talk a little bit about in the end, which accelerates your production screening process and makes sure to keep those failures in-house and also gives you very good feedback for improving your manufacturing process, the same way the HALT process improved your design process. So what happens is that infant mortality period becomes smaller. Now, with the wear-out process, you've seen under very accelerated stresses, parts wear out very quickly. And you've had a chance for feedback to see how you can extend that. And this normally would have happened over many years of field data collection and processing to see opportunities to improve wear-out. But now you've done it in a very short period of time. So now that wear-out time period has pushed farther out. During the useful life period, you've increased your margins, as we saw in that previous stress diagram, to where you now will have a lower steady state failure rate during useful life. So our new bathtub curve looks something more like this lighter blue line. So you can see we've significantly improved the performance in all three phases of the bathtub curve. So Qualmark manufactures HALT chambers, and the HALT chamber is a very common tool to use for doing this HALT investigation. Some of the critical parameters of it are the fact that it has 6-axis vibration, and I'll talk a little bit about why that's important. It has broadband frequency, which means multiple frequencies of vibration being put in the product at the same time. This is done with pneumatic hammers, which has shown to be the most reliable and consistent way to do it. For temperature control, it has liquid nitrogen cooling. This is different than other temperature chambers that may use compressors. Now, the reason why I've gone this extra step to do it with liquid nitrogen is for the ramp rate. You want to be able to change the temperature as fast as possible. And with compressors, it's a much slower transition. And going up in temperature, very high power electrical heaters. Now, one of the reasons for this is if you think about the type of stress that's created in thermal conditions, the mechanical stress that can be created with elements that have different thermal expansion coefficients that are in contact with each other. As they expand at those different rates, they create tremendous mechanical stress. Also think about components that have significant mass. You will have a steep temperature gradient going from the inner part of the mass to the outer. So here we are creating very intense mechanical stresses with temperature because we're able to do the ramp rate so quickly. These are some photographs of some units inside a chamber. You can see here that they are bolted to the table. They're fixtured with rods and beams. And the table itself is a very impressive piece of technology because of the composite structure that ensures you're getting that vibration energy all the way up to the product and that it's staying as broadband energy. You can see in the second picture that the cover's been removed. And you can make modifications like this to the product to help get those hot and cold temperatures into the inner part of the product as quickly as possible. So let's talk a little bit about the vibration energy input and how HALT is different than other testing methods. More traditional vibration testing methods might be done with an electrodynamic style table. And this is a table that has a coil and magnet. And when the coil is activated, you get a linear motion in one axis. And you set a frequency that you want it to operate at. This is very much like how a speaker works. Now, with a HALT test, what you want is you want motion in all three axes, X, Y, and Z, and you want rotation around those axes too. That's much more energy, and you're going to be hitting sensitive areas in each axis. You also want the frequency to be broadband. You want to have multiple frequencies at the same time. Now, this is important because different components have different natural frequencies, and you want to hopefully hit those natural frequencies to expose the failures. A good way example to demonstrate this concept is if you, let's say, take a vehicle that you've just designed and you built the first prototype, and you want to try to understand what components don't fit well together or aren't going to stay well together or where your weaknesses are. If you went around the vehicle with a hammer and just hit different parts with a hammer, you may find an area where something doesn't sound right or something comes apart. And if you were to compare this to, instead, taking the vehicle and driving it down a very bumpy road with big potholes, going off-road with it, and at the end of that process evaluating what occurred, you're going to have found a lot more defects. Well, the difference is when you went down that bumpy road, you were getting input in multiple axes and rotation around axes. You were getting a lot of different frequencies, and you were able to find all these failure modes in a much more compressed time, as opposed to hoping to hit the right failure mode with that hammer in that axis and expose it. So you can see how this greatly compresses test time and also helps you have these failure modes come to the surface very quickly and ones that may have been missed otherwise. Now the thermal portion. There are three key thermal parts of the HALT protocol. You have the hot step stress that will run it up in increments, usually about 10 degrees C, until you hit a operational limit and then ultimately find that stress limit. You will do cold step stress, same method, but going down in temperature until you're getting a response from the product. Now rapid thermal here, you can see that's the one where I was talking about, where you're hoping to use the expansion coefficient differences between different materials and the mass to expose mechanical failures. So these three steps each are critical, and you also will ultimately use them in combination with vibration after the independent vibration steps are done. And this will, of course, in combination, create a much higher stress level. Now, when trying to incorporate these HALT methods into a product development program, the people you'll be trying to influence to incorporate this are likely going to be driven very intensely by schedule. And if they do see the benefit and want to incorporate this, they're very likely going to say, can we do this at the end? Let's do this when we're getting closer to production and we have a lot of units to use and we have a little bit of time there to do evaluation. There's a problem with this, and the best way to describe it is the rule of tens. The best time for HALT is when prototypes are first available. So this, of course, is going to be something you have pushback on, because prototypes usually have a lot of allocated responsibility. They want to use them for demonstration. They want to see if it does design functionality. They probably also need to be used to see how it fits with other parts of the process. So the rule of tens is this. For every phase later in the development process, a failure mode is identified, the cost to correct it is 10 times greater. So that means if you find an issue early in the process and you were to find that exact same issue instead 3 phases later, it would cost you 1,000 times more. Now, it sounds like a lot, but it's actually, when you look at it, a very conservative estimate. So let's take a look here. This is a chart showing the rule of 10. You can see here in the bottom we have major program phases. You have design, you have integration, validation, releases, and then in the customer's hands. So let's look at what could be a simple fix in the beginning, a $30 fix. Something like you find a defect and you make a change to the CAD model and the rapid prototype. Maybe you want to change a plastic component. And you can obviously do this very easily, very little engineering time. And next time you make a rapid prototype, it's including that change. Now let's imagine you find that same defect much later when you're in, let's say, the validation phase. To change then, you're going to be re-cutting molds, the actual long-term production molds, which can be very expensive. A plastic mold can easily be $20,000 or $30,000. This then, once you get to the point of release or it's in the field, you can imagine when you're trying to find a field failure, there's an investigation. The product is no longer in-house, so you have to use people outside, service, or have engineers go out and try to understand the problem, root cause it in a remote environment, ultimately bring that back in, continue with the team there. The team ends up stopping doing work on developing the new products because they're now trying to deal with a legacy issue, make the changes, and you obviously are going to have stock that might change. So you can quickly see how something like a $30,000 response to the same issue is actually quite conservative. It could be much more. So you can see how the case for doing HALT as early in the process as possible, how it ends up with the same steps having a great deal more value to the program. So let's start looking at ROI here. When you're asking for HALT from the program, you're asking for engineering resource. You're asking for product that will be damaged and unusable for other demonstrations. Usually when prototypes are first made, there's only a few. You'll be potentially adding program schedule time early in the project when it's critical. And all of this is money. So what does the company get in return? Let's take a look. What you get in return is you get a mature product at release. So this traditional process of field failure investigation and redesign is minimized. So now if we are really honest and that in a product development program schedule include that time, which very much doesn't often get included when a program's advertised to have a certain schedule, you can see how this can save you time. So we're asking to add a step that may be looked at as adding time to the program, but actually is removing a significant portion of time at the end of the program where field failures are being addressed and fixed. And there is the engineers being available to continue with technology investigation. Those engineers are much more valuable inventing new technology and progressing the product line than they are just solving and root-causing field issues. It's not a very efficient use of their time. With the HALT process, you can end up with earlier time to market because you've matured the product early in the process, and the changes that you're implementing from that rules of 10 are going to be easier to do, faster iterations, which then leads to being the leader in the market with new technology. Brand perception. Be the industry bulletproof benchmark. When a customer has a product that functions well in conditions that they consider that far exceed what they expected the product to work in, you get that bulletproof label, and that can be a very powerful thing for sales and market share. And of course, using customers as test engineers is a horrible idea. And in effect, that's what we do with a lot of traditional programs. The customers are very bad at being test engineers. They don't write reports. They don't give good insight or even keep the product a lot of times. And they also are frustrated, and that's not something they want to do, and that's going to hurt your brand. The final phases of development will have reduced cost. Those late program design changes can have a huge impact. And not only in time, but you might be scrapping a large population of manufactured components. You'll also be able to have lower pre-production volume needed for testing and demonstration because the design is mature for a lot of the later reliability and system tests. If you are going to be doing reliability testing that's demonstrating life or helping make MTBF statements or showing when wear out occurs, if you have a product that can successfully go through these tests and make these demonstrations earlier by having less failures, you'll be doing it quicker and with less product. And as I mentioned, having that design team progress and fully use their capabilities that are being paid for by the company to invent and to advance technology is a very big advantage. Picture that over a 5-year period, how much farther along your company's knowledge would be. So let's try and put some actual numbers to this. Let's look at the quantitative value. So HALT adds value to the product by reducing non-recoverable engineering costs. It can reduce warranty costs in the field, and it can reduce manufacturing costs. So let's look at a little case study here. Let's say we have a home electronics device. Let's say they manufacture it at a rate of 15,000 units per year for $70 a unit. And let's say its current performance is a reliability of 96%. So design engineers investigating and solving an issue in the field, there has to be a root cause process done. Let's say this takes 60 man-hours. They have to communicate with service and the customers, meeting with the team, design, doing testing, and re-release. So if the engineering cost per hour with overhead is $75 an hour, the NRE could easily be $3,000. So if this also leads to retooling, that might be another $15,000 in retooling costs. For warranty, each failure mode effect could easily be 1.5% of the production population. So 1.5% of 15,000 units is $70 a unit, is $15,000 a year. So the NRE tooling and warranty per issue found in HALT could easily be $33,000. And HALT commonly finds 2 to 3 critical issues like this in the prototype stage that can be easily fixed in this stage. What about manufacturing cost? It's going to reduce sensitivity to manufacturing variabilities. If manufacturing control and precision can be held at lower levels, you can have a tremendous reduction in manufacturing costs. So let's say a 20% reduction in manufacturing costs is done because of the HALT changes. And we end up with a reduction in 50 cents a unit from a simpler manufacturing process. At 15,000 units a year, that's $7,000. Now, as I mentioned earlier, HAS is a manufacturing screening process that can yield tremendous ROI benefit, and HAS can only be done after HALT is done. HAS can easily reduce manufacturing, testing, and inspection time and cost by 85%. So for a $70 retail unit, let's estimate $1 test, inspection, and scrap of the total cost. At 15,000 units a year, it's $30,000. So for the 2 issues. So reducing this expense by 85% is a savings of $13,000. So in our case study, we found 2 issues. One can be, let's say, solved by changing the shape of a plastic part. The second issue can be fixed by changing, let's say, a PCB layout. Each issue was 1.5%. The new reliability will be 99%, so that alone creates a tremendous amount of benefit. And your total NRE warranty and tool savings cost was $67,000. The manufacturing process and yield benefit was $20,000. This is $87,000 benefit from the program. So let's look at the actual cost of doing that HALT program. 3 days of HALT chamber lab time is usually around less than $10,000, we'll say $7,000. 3 to 5 product prototypes used, effectively consumed, and not able to be used for other testing. For a device like that, it could be about $6,000. 5 days of design engineers' time to attend the testing and do the redesign, we'll say that could be about $3,000. So the total expense of the HALT testing is around $16,000 in this case. So $16,000 of expense to gain $87,000 of saved expense. That's about a 5 times ROI on a HALT test for that device. So you can see how significant it is, and hopefully see in the example I did that I was being pretty conservative. You can probably imagine, depending on the complexity of your product, how these numbers could be much larger with a much bigger ROI. Now the example I just did is with using an outside HALT lab. What about bringing HALT in-house? When do you want to start looking at that and the benefits there? Typically, I would say a rule of thumb is if you're doing more than 6 HALT tests per year, do an ROI calculation based on recent results. A good target would be to look for a 3-year cost crossover for the capital investment. So a mid-sized HALT chamber installed, depending on your existing facilities, could be around $185K. LN2 consumption for a HALT program could be about $150 a week with an $800 a month LN2 tank and infrastructure system lease. That's a 3-year expense of about $235,000. So completing 6 development HALT tests per year outside, you might have saved about $522,000. So that's an ROI of about 2 times just in that estimation. What about the qualitative side? You're going to have much better root cause analysis with a full engineering team being close to the HALT test. So if you think about the fact that the HALT test is exposing failure modes to be analyzed, doing it off-site, engineers have to be there to do that work, to do it effectively. So you're probably only going to have 1 engineer of a specific discipline or 2 engineers or 3. Now imagine if the entire design team with all the engineering disciplines are right down the hallway. That's a big improvement in root cause analysis and what you get for the HALT testing. More HALT testing will be done when it's so easy to do and the equipment's available. You're going to do it on more products and more systems and find more issues that you get benefit from. Now release products. What if you're investigating failures in the field and you have the HALT capability in-house? You're very likely going to use this technique to help do your root cause analysis, so it will help with release product investigations and accelerate those as well. Now with all this, your lessons learned database is going to build much more rapidly than it would traditionally. Think about all the things you will find in relationships between stresses and failure modes that you'll be using in your new product development. Now, there's also the benefit of how does HALT enhance other reliability and engineering practices. So let's talk a little bit about the systems engineering side. The definition of reliability integration is the process of seamlessly and cohesively integrating reliability tools together to maximize reliability at the lowest possible cost. Some other common reliability tools are failure mode effect analysis, FMEAs. These are used to identify areas of high system criticality. And this is process, you have all the different engineering disciplines in the room hypothetically coming up with potential failure modes. They are identifying how severe the failure modes are. This is done by how critical it is. This is looking at the likelihood of occurrence and how detectable it is. So when you're done with this process, you have a list of the most critical areas for your product. There's design of experiments where you are creating experiments that are specifically looking for what is affecting the performance of the product, what inputs can be controlled or not controlled, interactions between these variables. And there's stress strength analysis, which is done on products to understand the margins and inconsistencies. Now, each of these can be greatly enhanced with HALT. And also feeding them in with HALT can greatly enhance HALT. So looking here at a simple breakdown of a possible product development program, you have your concept phase, design phase, prototype phase, and manufacturing phase. And I've kind of put a few arrows on here showing some of the interactions between these. And HALT being in there can further make these other tools more effective. Now I mentioned HAS earlier. I wanted to, finishing up, talking a little bit about HAS and HASA. HAS is a highly accelerated stress screen. In HAS, all products are screened at stress levels well above the operating levels, and these are applied to quickly uncover process weaknesses, and it's going to reduce quality-based failures. HASA is a highly accelerated stress audit. This is a similar process to HAS, but it's only done on a statistically significant portion of the population. So in that case, once you have HAS and you have it dialed in and you have it well controlled and you understand your product too and have improved your product based on this, you now can do it in an auditing fashion which even further accelerates how quickly it can be done and improves the time of manufacturing. So HAS will detect and correct process changes that will reduce production time and cost, increases out-of-box and field reliability, dramatically can reduce field service and warranty. Infant mortality rate can be kept in-house entirely, and also while discovering it in-house could then be root caused and eliminated. And this will find failures not done in traditional burn-in type tests. Now, burn-in type tests, as we know, are where the device is effectively run in more of a normal operating condition, and you are looking to hopefully expose defects in that process. But you can imagine with HAS, where you'll be finding many more of these much earlier. And the important thing here is that HAS cannot be done without HALT. You cannot create a HAS protocol or process without HALT. HALT's the foundation for this. So here is further ROI on having a HALT process. This will lead you to changes in manufacturing screening that significantly improves your brand product that is out there in the field and also reduce your manufacturing expense. So there's even further return on investment for the company. Let's take a look on that stress chart again, what a HAS stress range would look like. You can see here that the red section is an environmental stress screen that may be applied in manufacturing. And this would be within product specs. You'd be looking to see if this product is being used in the field right away. Is it going to perform as intended? Now the problem here is you're not going to be catching any defects that are outside that range that in later parts of life could actually become operational defects. So the HAS stress range is within the operating limits but outside the product specs. Now to select this, obviously you're getting into an area where you have to understand exactly what you're doing. So that knowledge comes from the HALT testing. And you're able to select the test range that will not use up too much product life or not expose failures that are not significant, but will ensure to capture all defects that could potentially lead to failure modes and do it very quickly. So as a derivative process, again, HALT has not only given ROI based on its immediate design improvement process, but it's laid a foundation for understanding your product well enough that you can add other processes. So HALT must be done first before all these other benefits we talked about. And it's very easy to not only demonstrate the initial ROI with actually quantitative costs, but you can see how it can support other product processes and benefit other parts of the organizations. Now, the cost-benefit comparison for HAS, you have to have purchased the in-house HALT equipment. This would be difficult and very expensive to do with outside HALT equipment. You have to have manpower to run the test and do the root cause analysis. And you'll be consuming liquid nitrogen and electricity, which is part of your facility overhead cost, so those have to be estimated. But the benefits, faster production time from faster screens, bad product staying in-house, and the ability to quickly identify and root cause production issues. So the numbers done for the ROI and HAS will be based on those costs and benefits. So in summary, the ROI of HALT early in the development program is significant. You'll have fewer design iterations, you'll release a mature design, lower warranty cost immediately after launch right away. You won't be waiting for that maturity process to be happening in the field. Reducing manufacturing costs if you use it as a foundation for other tools like HAS. You have improved efficiency of engineering resource. You have these advanced engineers with a lot of skill and the ability to advance products that won't be spending their time doing root cause analysis on product defect. Instead, they'll be innovating for you. And you have the opportunity for implementing these other practices that will be based on what you've learned with HALT and the technique that's now in-house. Thank you very much for your time. I'm available for any questions, comments, or to learn more about your product and company. You can contact me at apexridge.com, or you can email me at this contact information. And I look forward to helping you with any of your reliability needs. Thank you.
Thank you so much, Adam. We do have some questions that I'm going to relay to you, and you can address them. The first is, are there more case studies to support the rule of tens?
Yes, there's many. And I would imagine you'd be able to find that in-house. I mean, you could take a recent product development failure that was found while developing a product and estimate the cost it would have been to have found that at the earliest possible stage, at prototype or even before that. Now, take a recent field failure that you have experienced and, estimate the cost on that. I mean, it involves a lot more people, probably even travel and interaction with the customer, bringing that back in-house, and how long that process takes, how many more man-hours. So it's probably very likely you could very easily do that even with your own product and recent experience.
Okay, thank you. And the next we have is, does HAS take life out of the product and thus cause it to reach end of life sooner?
Well, you have to be very careful with that because you are putting very excessive, very high stresses on your product in HAS, and you have to make sure and constantly monitor and update your HAS process to ensure you're not doing that. That is a very obvious risk of doing it. But if done right, you will not be taking life out of your product that you've promised your customer that they have.
Okay. The next one we have is, you say that HAS cannot be done without HALT. What if I have a product already released and has years of field data?
No, you cannot. You absolutely cannot. The field data is the product being used in that operational limit. You have no knowledge of how the product responds outside those operational limit stresses. And that information is the foundation for developing the HAS program. The only way to find that information is to actually take your product through extreme stresses in a HALT test.
Okay. How do we determine the lower and upper limits for HALT assessment with respect to temp and vibe?
Well, you actually do not determine those limits in advance. You effectively, the limit of where you go with your test is how the product responds. Remember, the purpose of the test is not to compare how the product responded at a specific limit. It's to expose the failure mode and have a chance to observe it and root cause it. So you're going to continue to increment the stress until the product responds at its operating limit and ultimately destruct limit. So for the test, you effectively are going to go either as far as the product can or as far as your test equipment can go.
Great, thank you. Does HAS require a different test chamber, or can HAS be performed with different settings on the HALT chamber?
HAS typically is performed in different settings in the HALT chamber.
Hallmark also has the only HAS dedicated chamber in the industry as well. That's our Q-Fusion system. If you'd like to learn more, it's prominently displayed on the Qualmark website. Next question, can we get a copy of the presentation? Yes, you can. That will be deployed at the wrap-up of this webinar, so please stay tuned, and you'll have a link to the playback presentation as well as a slide deck. So can you get frequency-controlled vibration profiles like swept sine on HALT chamber? No,
you can't. The HALT chamber has been very specially designed to ensure and to create and ensure what gets to the product is broadband frequency. So because it's been designed this way in the physical structure of it, you cannot do specific sine sweep type vibrations. For that case, you would want to have more of an electrodynamic style vibration table.
Okay, how to cover humidity failure with HALT testing? I guess how do you...
It's important to remember that HALT testing doesn't have to be limited to temperature and vibration. It can be any stress that you believe can induce a failure mode. It can be high voltage. It can be humidity. It could be, salting, other corrosion exposures. It could be high impact. So it's not limited to temperature and vibration. It's wide open to whatever you feel is going to expose a failure mode that's worth investigating.
What life percentage of a product should a proper a proper HAS profile be able to take?
I'm not sure if I understand the question exactly, but you should not be consuming life that is expected to be part of the intended useful life of the product when it's manufactured and distributed.
I've heard the term tickle vibration used by HALT techs. Any idea what this is?
Yes, absolutely. It's actually a very important step to do. Tickle vibration is about, let's say if you had an electrical PCB board and the failure mode was, let's say, a fracture in a connection in the board. If this fracture was created, let's say at 30 Gs of vibration, and you might actually not see the response in the system from it because the vibration, even though it's created the crack, is so intense that it's keeping the connectivity across that crack working well because it's keeping the points in contact so frequently. So you've created the failure mode at 30 Gs, but you're not going to be able to observe it clearly. So what you can do in your protocols at the higher vibration level steps, you stop after each step and go down to maybe a 5G vibration, which is called the tickle vibration. And what will happen is this lower vibration is at a low enough energy that the crack will be exposed and you will see an issue with the system. So you've created the failure at a high level, difficult to observe, but intermittent to those steps, put in a very low vibration level, which allows you to see that the failure has occurred.
And in that vein, if you want to learn more about the guidelines for HALT and HAS, you can find those in their complete content on our website in the resource section as well. So that's a very usable tool. Next question, is it mandatory or highly recommended that the device be powered and running during complete HALT test?
Yeah, that's actually very important because, again, we want to, during this test, to see how the product's responding because that's when we know a stress has created a failure mode. So you want the device to be operational and using as many facets as possible so that you're monitoring fully how it's being affected.
What are rules for design improvement?
Some other rules for design improvement, the reliability toolbox is very diverse. There are a tremendous amount of things that can be done. Of course, this is where a lot of good expertise and help can be very useful because you want to, of course, select the right tool for the job. So you have to understand in your product where your number one concerns are and use the right tool. So for instance, an example might be an FMEA. It's a very powerful tool for the phasor at where the team is coming together, all the different disciplines, and they're discussing and looking at hypothetical failure modes and realizing which are most critical and where they should put their engineering resource. Because you have limited resource, limited time. You want to make sure to go after the most critical items. I actually recently wrote an example in my blog on my website about a Nazi submarine in 1945 that just about 20 days before the end of the war sunk because the toilet was flushed. And I show how an FMEA would have very likely mitigated this failure mode because basically if the hydraulics engineer and the electrical engineer had been in the same room and discussed some hypothetical failure modes, I think they would have seen this failure mode very clearly. It sounds funny to say it was a toilet, but it was a very big deal from a stealth technology standpoint because submarines had a surface for the toilets to be used because of the high pressure when they're at depth of the water around the submarine. So being able to use it, the toilet, when you are at depth would reduce the amount of time you'd have to surface and obviously surface at critical times. Well, it actually failed in a way where it flooded because it was a brand new technology, had a very complex process to be used. It flooded, the toilet was right over the battery pack. Put water on the battery pack, which released a very toxic gas, and they had to surface immediately. They were sighted by a patrol, and they were bombed and sunk. So, putting something that's extremely highly to leak over something that's extremely sensitive to water, obviously, if you had these different engineers in the room thinking about failure modes, that would have come up. So in that case, an FMEA would have been an extremely valuable tool.
Can higher input voltage be used as an alternative to physically loading an electric motor, for example?
I wouldn't call it an alternative. It's another stress. You want to come up with as many stresses as possible to make it fail. a lot of times when I'm educating people on HALT, I say, well, just tap into your inner 6-year-old. What would that kid in you have done? We're all engineers. We're all had that base curiosity about how things work. And when we were kids, the way we found out how things were worked is we took them apart and we smashed them and found every way to break them. And you learned about them. And you're effectively doing that process in a little more formalized manner. So in addition to things like vibration or temperature, doing high voltage, to call it voltage breakdown in something like a motor, would be a very good method to use.
Do you recommend a certain type of accelerometer for HALT to get the most accurate results?
Usually when you go to do a HALT test, the lab has accelerometers that they use. A lot of them are piezo-based, but it also can develop on the product and how you want to mount the accelerometer. So it's going to be very likely that the HALT lab that you use is going to have all that equipment and be able to use their expertise to make sure you're monitoring your device in the best way possible.
Is there any way to measure if the maximum table vibration is being transferred directly into the product or device under test?
Yeah, it's actually very important. And again, this is where the expertise from the outside lab will be very helpful. They're experienced test engineers. You not only monitor the vibration of the table, but you monitor vibration on the product at the key points. So you'll have many accelerometers involved in the test. And you can see right away how much energy is getting into their product and where it's getting into. And that might, drive you to change the way it's mounted or to change, the assembly itself even to try and get energy into the areas that are most critical.
And do you ever use a precipitation screen, and under what conditions would you use or not use it?
Yeah, you absolutely would use a precipitation screen. For those that aren't familiar about that, that's something that's used in HALT HAS to change, a detect, which is latent or undetectable, to one that is detectable. So something like a poor solder joint could be an example. So you definitely would use this, and in some ways this is similar to the idea of the tickle.
Alrighty, well, I think that's all the questions for now. Thank you very much, Adam, for taking the time out of your busy schedule to present today. And just to remind everyone, Adam's reliability expertise extends across any industry, and he's a tremendous resource for any of your organizations. So if you'd like to speak with Adam, the contact information is listed there on your screen. You will also, again, be getting a link to this, and we'll have his contact information there. You can also reach out to Qualmark by visiting our website, dialing the toll-free number that's listed, or sending an email to coe@qualmark.com. And I will put you in touch with Adam. And thanks everyone for attending the presentation today. Please visit our events page on the website often to keep abreast of all of our upcoming free webinars, and browse the resources page to find a wealth of archived webinars on other topics, white papers, articles, and other helpful tools like those HALT and HAS guidelines that I referenced previously. And we appreciate your attendance and encourage you to keep joining us for these useful webinars. Thank you, Adam, very much.
Thank you very much, Cami.
Bye-bye.